Good day, everybody. Today we're going to look at what optimization each apportionment method has, at least with the major apportionments. So I've got the apportionments for several years here, 1990 through 2020, using the official census data. And right now we're looking at 2020. And we're going to look at the apportionment using and compare if we use Hamilton's method or Adams' method, Dean's method, rounding by the harmonic mean, Huntington Hill's method, rounding by the geometric mean, Webster's method, rounding by the arithmetic mean, Jefferson's method, where Jefferson and Adams you round by the min and max of the two numbers. And we also look at some other ways we can find the mean, just to have more comparison. So when we do the optimization, we're going to throw in some extra apportionments here. Just a quick review. Here we have many popular means, starting with the arithmetic mean, the one that everyone really knows. But of course there's many other useful ones. The geometric mean, multiply two numbers, take their square root. Harmonic mean, that's sort of like averaging the reciprocal of the two numbers and then taking the reciprocal of that average. The Heronian mean, contraharmonic mean, root mean square, centroidal mean. Basically, to be a mean, you have to satisfy a few properties. Homogeneous in that if you multiply each number by some value k, then the mean would be multiplied by that value k. It has to be symmetric, so it doesn't matter what order you put the numbers into the formula. Also, the mean must be between the min and the max, and we'll go inclusive. And notice the min and the max then also satisfies these two properties, so the min and max are also means. Again, we looked at this before, but we'll take a quick look again. For those means we just saw, they're kind of neat in the trapezoid. The harmonic mean will pass through the intersection of the diagonals. The geometric mean divides the trapezoid into two similar trapezoids. Let's look at the trapezoid here. There it is. So if you have two numbers, and we'll represent the numbers by lengths, then you can make a parallelogram, right? So in this instance, A is a bigger number than B. They're both positive. But if you make the parallelogram, if you make the diagonals where they intersect, this vertical length would represent the harmonic mean. This vertical length, that's what makes these two resulting trapezoids similar. The Heronian mean, just 1/3, that's kind of boring. Arithmetic mean, that's half, which we kind of know. The centroidal mean passes through the centroid of the trapezoid. The root mean square bisects the area. So there's as much area on this side as there is on that side. And finally, the contraharmonic mean, well, it's as far to the right of the arithmetic mean as the harmonic mean is to the left. That would be assuming you had the numbers in order of smaller to larger. This diagram actually has the larger number on the left, but if you flip it so the smaller numbers on the left, then the contraharmonic means is as far to the right of the arithmetic mean as the harmonic is to the left. Anyway, so, and again, here's all the means. The Gauss arithmetic geometric mean wasn't in that trapezoid, but basically repeatedly take arithmetic and geometric mean of the two numbers, and then you get two new numbers, and you keep doing arithmetic geometric mean, and then it's going to converge to this mean right here. Anyway, so here they are in order. So if you have two numbers, now here the two numbers are consecutive integers because that's the way we have to do things on our apportionment. Then here's the min, there's the max, and of course the arithmetic mean is just exactly halfway in between. The geometric mean, if you multiply the two numbers and then take the square root, you get those values. Harmonic mean and so on. So there is an order. We saw that in the trapezoid, except this mean wasn't in there, but the means are guaranteed to be in this order. And notice if I multiply, say, by 10, so the mean of 1 and 2, I'd have to scroll back up, but the means here are exactly 10 times the means here. Anyway, so back to my apportionments. Here we are again with 2020, and just using these divisor means and Hamilton. Hamilton's not a divisor, apportionment, I should say. You generally get different apportionments for different rounding methods, but here there was a lot of similarity. In fact, Hamilton and Webster was similar as well as all of these. If I look at 2010, now Hamilton and Huntington Hill match. Webster is a little bit different, and so on. So you got all these differences. Dean's different, of course. So we will be able to compare some optimization properties here. Let's see, Hamilton is unique, but Huntington Hill and Webster ended up being the same, interestingly. In 1990, Hamilton was different than Huntington Hill and Webster, which was, and these are different from each other as well. So 1990 I'll keep looking at just so I know Hamilton's different than Huntington Hill, which is different than Webster, and so on. One other apportionment which didn't happen, but back in December of 2020, before the census came out, I did an estimate of what I thought would be the population, and of course I wasn't correct. And I wouldn't show it, except the apportionment that I picked, it ended up being that these means, namely the Gauss arithmetic geometric mean, was different than Huntington Hill and Webster. So I thought it was interesting that we had a mean in between Huntington Hill and Webster. All the other apportionments, these two are either the same as Huntington Hill or they're the same as Webster. But this hypothetical gives me one that's different than those two. And it's different than Hamilton. So it'll be good to check the optimization on this one as well. So let's look at the apportionments here and their optimization. First, let's see. Webster is the same as these two, so I will hide them. And the same as these two, so I'll hide these two. So I can fit more in. This is for 2020. Do the same in 2010. Here Gauss and the Huronian mean matched Huntington Hill. And the centroidal and root mean square matched Webster. So these are the unique means, apportionments. Here there was a lot of matching with the Huntington Hill method. In fact, I might as well get rid of all of them. Right, so Huntington Hill matched with all of these. Interestingly, Hamilton was different. And then lastly, in 1990, Gauss and the Huronian mean matched Huntington Hill. And the centroid and root mean square match the contraharmonic. So these are unique apportionments. All right, so the first thing we'll look at is how many people per seat we get with the apportionments. So I've got the population right here of each state, and what I'm going to do is divide that population by how many seats each state would get depending on the apportionment. So with Alabama, every apportionment gave Alabama 7 seats. So this population divided by 7 is roughly that number. It's rounded, but that's enough digits. Except for Jefferson. Jefferson would have only given Alabama 6 seats. So if I divide this number by 6, it's a higher people per seat. And so you just do that with each state and each apportionment, and you get how many people per seat each apportionment would give. Now, Adams is guaranteed to minimize the maximum of your people per seat and the average statewide. And that seems like a good thing to minimize, but it's not necessarily. And well, I mean, if you look at the apportionment, I mean, you can see like California should probably fairly get 52 seats, but Adams only gives it 50. In fact, the larger states lose out. If you could give fraction of people, Florida would get 28.34, but instead it only gets 27. And similarly, I think Texas, 38.34, but only gets 37. So it's not the best method, even though it looks good in this optimization criteria here, where just minimize people per seat. Notice with, say, Delaware, its standard quota is 1.3, and 1 seems to be pretty fair to give Delaware. But if you give Delaware 1 seat, its people per seat then, well, its population 990,000, that would be its people per seat. What happens with Adams' method is whatever divisor you use, you're guaranteed to never be above that. So none of these will be above that 802,000. In fact, I could have used other divisors. There's a whole interval, but I used 802, so every state was below that. In fact, the maximum was 801,421. Looking at the average for the country, that's this standard divisor where you take the country's population divided by the number of seats, 435, you get this. So that should be the average for the country. Now, some states will be over that average and some will be under. Right, let's look at, say, Webster's method. Right, again, Delaware at 990,000, that's over the country's average, and other states are under. Like Connecticut is under, and so forth. If we look at just how much each state is over, but then if it's under, you don't worry about it, we get this next group here. So if you're under the country's average, it's a 0, but if you're over, how much over the country's average are you for each state? So that's what I have here. So only count how much you're over that amount. That's what we have here. And again, Adams will minimize that sum. If I look at other years, I won't look at every year, but maybe let's just go to 1990. Again, take the country's population, or the state's population, divide by the apportionment, or the number of seats for each apportionment. Then Adams will minimize the maximum there and the average. So in 1990, the population was a lot less, so the number of people per seat average was a lot less. And if we look at just how much you're over the country's average people per seat, again, Adams will minimize that. Which seems nice, but what's really going on is each state only counts one time. So for example, with California, you can be over the country's average by, say, 24,000, and you can do that because California is so big. Dividing by 52 or 51 or 50, you get similar numbers. It goes up a little bit, but not too significantly. But it only counts once. If I think about how many times should it count, well, with Adams, there's going to be 50 congressional districts, if we used Adams' method, that had that amount where they're over the country's average by 24,000. I'm still in 1990 here. Let me jump to 2020. Here we go. So same thing here. I mean, California, big state. Everybody wanted to give California the 52 seats except for Adams. So it was over, which isn't too much, but again, it only counted once as a state when I do this sum. But there's going to be 50 congressional districts really that are over by that average. At least the average of those 50 congressional districts. So if we multiply all these numbers here by the state's apportionment, by the given apportionment, the number of seats by each apportionment. So for example, multiply this number by 50 over here. This is for Arizona. Multiply all these by 9. Look like everybody decided to give Arizona 9. So multiply this by 9 for everybody, and so on. Then we get this value. This is the 50 times the 30,000, or whatever it was. So now it's more significant if you're going to count all the congressional districts that are over. And so now if I sum this, Hamilton is actually guaranteed to have the minimum there. So we can see Hamilton's the min. If I go to 1990, this is the 50 times the, I think in this case it was like 24,000 or something. In other states were over, but so just multiply how much you're over the average by how many congressional districts there were. Hamilton will minimize that. I mean, it's close in some cases, close to Webster, but it was different. If I quickly look at 2000, where Hamilton was, again, unique people per seat, Adams minimizes that. How much you're over the people per seat average for the country, Adams will minimize that. You can see hopefully there. And now if I multiply each of these amounts by the apportionment, we would have Hamilton will win that. One more, the hypothetical. Just forgot to hide these here. So Huronian was the same as were these three or two. There we go. So the apportionment, the people per seat for the given apportionment, Adams minimizes that. How much you're over the average. If you're under the average, don't worry about it. Adams will minimize that. But if you multiply these numbers by how many seats, Hamilton will minimize that. So this is the maximum of people per seat for each state minus the people per seat of the country, or 0, whichever is bigger, so negatives don't count. And then if you multiply by how many seats each state got. Again, sometimes close, but whatever. Next thing we'll look at is, what if you did people per seat of each state minus people per seat of the country, but in absolute value? So before we only worried about if it was bigger, but now what if it's smaller as well? Just take the absolute value. How far away are you, bigger or smaller? So if you find that difference, people per seat of each state for each apportionment, how far is it from this average? Dean, or rounding by the harmonic mean, is guaranteed to have that smallest average and smallest maximum as well. There might be a tie, but you can't go smaller than this. And well, Huntington Hill matched it, but the average though, Dean was the smallest. So this is 2020. If I go to say 1990, again, so how far away each state, its people per seat from the countries in absolute value, just find that difference there. Dean, or rounding by the harmonic mean, is guaranteed to minimize that. So that's another nice way. So you want it to be as close as possible, each state, to the country's average. If I look at the 2020 hypothetical, same thing. Dean's got the minimum there. And looking at 2000, okay, same thing, Dean will win. But now we're going to do the same thing we did before, where, again, this counts each state as being 1. So when I look at California, it's people per seat and how much you're off, how much different you are from the people per seat of the country. Well, that's going to happen 50 times for atoms, or it's going to happen 52 times for most of these other methods. Looks like, well, it happened 55 times for Jefferson. So again, multiply this difference, absolute value difference, by how many times it happens within each state, and now what we get is that once again Hamilton will minimize that. And so here's the average, and so I divided by the 435 seats there. So on average, each of the 435 seats will be maybe that far off from the people per seat of the country. This is 2000. And that's the minimum. If I look at it for each state, for each year. So we're at 2020. Hamilton will again minimize that. So this was that people per seat, absolute value difference from people per seat for the country, the state minus the countries, times the number of seats for each state. I should note some of the notation I use. S will be the number of seats for the country, so 435, and P, the population of the country. And then for each state, we'll call it S sub k, the number of seats given to state k, and P sub k, state k's population. So if you can read that here, it's the state's number of seats times that absolute value difference. Use Excel. Hamilton minimizes that. In 1990, again, the minimum, and it can be pretty close for some of these middle divisor methods, but Hamilton is guaranteed to have that minimum. which is a nice property to have. For the hypothetical, again, pretty close, 19832, 19826, but Hamilton does minimize. And then, of course, if Webster happened to match Hamilton, then Webster will end up being the winner, but only because it matched Hamilton. When Webster is different, as in 1990, Hamilton is better than both Webster and Huntington Hill. So again, that's the number of seats times the absolute value difference there. Not as obvious of something that you'd like to keep small, the people per seat, but the reciprocal of that, the seats per person, you might want to minimize as well. That's more for other states. So you don't want any state that has overrepresentation. I mean, a simple example, if there's one representative for 10 people, then each person has 0.1 of a representative. Whereas if you have one representative for 100 people, then each person has 0.01 of a representative. So that other person's kind of unfairly overrepresented. And so you kind of want to smooth that out as well. Jefferson's method is guaranteed to minimize that. So if I take these reciprocals, we're dealing with scientific notation, but the smallest number is given by Jefferson's method for the maximum and for the average. Similarly, with the Adams method, if we take how much we're over the country's average, so only worry about if you're over, but if you're under this country's average, don't count it, then we get the following right here. Jefferson will minimize that. And again, it's actually a nice property, but then again, looking at Jefferson's method, maybe it's not so nice. But as Adams did, I mean, again, we're only counting California one time. So if I multiply each of these amounts, so this is seats per person, or 0, whichever is bigger, how much you're over or bigger. Well, if I multiply that by how many people are in each state, then we get this. And once again, Hamilton will minimize that. So this is just the sum there. So the number of people in each state times for each state if you're over the country's average of seats per person. Your seats per person minus that, or 0. So if you don't multiply the number of people, Jefferson will minimize that. But if you multiply by the number of people, Hamilton will minimize that. Again, 1990, Jefferson minimizes. Just worry about how much you're over. Jefferson will still minimize over the country's average, but multiply by the number of people in each state times how much you were over. Hamilton will minimize. 2,000 seats per person, Jefferson. How much you're over the seats per person of the country's average, Jefferson will minimize that, but multiplying by number of people in each state, Hamilton will minimize that. For the hypothetical, 2020, no surprise. How much we're over the country's average, but now multiply these numbers by each state's population. And again, Hamilton will minimize that. Again, this is just to throw in the extra, this Gauss arithmetic geometric mean. Pretty close, but it's higher than Hamilton. which matched Webster. If we take absolute value difference, just like we did with the Dean or harmonic mean average, when we did people per seat minus the country's average, the state minus the country's average, but absolute value difference. Well, if instead we do the seats per person for each state minus the seats per person for the country, find the absolute value difference, so count above and below. And here's all those differences, add them up. Webster is guaranteed to minimize that. So Webster's got the smallest, so to get as close as possible to the seats per person of the country's average, Webster will do that. In this case, Hamilton and Webster are matched, so they are identical. If you multiply this number by how many people are in each state, we get these values, and Hamilton's guaranteed to minimize that. Now here, Hamilton and Webster were the same, so we're not seeing anything, but you can see it's the smallest there. So that's the number of people times this absolute value difference. So let's look at some other years. 1990, so Hamilton and Webster were different in Huntington Hill. So seats per person minus the country's average, absolute value difference. The maximum is guaranteed to be minimized here. Again, there's a tie though, but the average, it's close. You have to go to a lot of decimal points here. Like 1.0098, 1.00969 times 10 to the negative 7, 1.01. So Webster minimizes that. But if we multiply by the number, each of these numbers by the number of people in each state, we get these values. And now Hamilton is guaranteed to minimize that. So let's look at 2000. Here, Webster and Huntington Hill were matched, but were different than Hamilton. Seats per person minus for each state minus the country's average. Again, guaranteed that Webster will minimize that, so it's smaller than Hamilton. But if you multiply each of these numbers by how many people were in each state, then we get these numbers, and Hamilton is the smallest. Okay, well, I guess one more, the 2020 hypothetical, just to make sure Gauss can't win or something. It's in between Huntington Hill and Webster. Seats per person minus for each state minus the country's average. Again, had to go out a lot of decimals there, but Webster does minimize that. But multiplying by how many people were in each state, again, Hamilton, which matched Webster here, but outdoes the Gauss, arithmetic geometric mean. One other thing Hamilton is guaranteed to optimize is if you look at the apportionment, or how many seats you give each state, for the different apportionments, how far are you from the standard quota? Right? Ideally, you know, if you're distributing a liquid or something, you could give each state this standard quota. But since we're distributing people, we have to go to the nearest integer. So how far is the given apportionment from the standard quota? Well, that's these values here. Hamilton, this wouldn't be too hard to show, but is guaranteed to minimize that. Okay, I mean, basically that's how Hamilton method works. You have the standard quota, and then you give out the seats based on, you know, if you're closer to the higher upper quota or not. So Hamilton minimizes the standard quota for each state minus the given apportionment to each state for these different apportionments. So let's look, say, at Montana. With Hamilton, if you give it 1, you're 0.426 is how much you're off. If you give it 1 seat, and it should have gotten 1.426. So Hamilton's right there, 0.426. If you give it 2 seats, then you're 0.574, right? So you're more away from the standard quota if you gave it 2 seats. So Hamilton's guaranteed to minimize that. Here's 1990. Hamilton being different than Huntington Hill and Webster. So if you find that difference for all the states with each apportionment, Hamilton's guaranteed to minimize that quantity. For 2000, Hamilton being unique here, didn't even match contraharmonic. Just find the apportionment minus, or how far are you in absolute value from the standard quota. So where are some differences? So Hamilton would give this state 4. 3 might seem smaller, but again, you have to do it for the country as a whole. So you gained a little bit there. Let's look at Utah. So the contraharmonic was smaller. Huntington Hill was smaller than what Hamilton was, but for the total sum, let's go elsewhere. They're different. Let's go up to California. Huntington Hill is bigger here, 0.553, 0.447. So the sum's going to be really close, average, but Hamilton 0.2334, Huntington Hill 0.2338. So a lot of decimal points there, but Hamilton will have the smallest average and the smallest max as well, right? So the max was a little bigger here, 0.553, thanks to California, 0.553. Lastly, for that 2020 hypothetical, just to throw in Gauss, I mean, it's not too big a surprise that Hamilton minimizes. Here it matches Webster, but again, pretty close. So the method used, Huntington Hill, so far hasn't optimized anything. So, why should we use it? Well, I'll show what it optimizes, and we can decide for ourselves whether that's the best criterion or not. It's kind of subjective, to be honest. First, if we want references, and I'll put these links in the description, but this is what we've looked at so far: SK, number of seats for each state; PK, the state's population; Adams minimizes, well, that's a different way of showing what I had. Dean minimizes that people per seat. This is actually a relative difference, but we'll show it also minimizes from the country's average. And again, so here's the this is a relative difference. That's one way to show it for Huntington Hill. Webster, the seats per person, relatively from state to state, but also to the country's average. And then there's Jefferson. So here's some of the things we put in other words, right? So that's sum with the max and so forth. For Hamilton, it matches the state's quota minus the standard quota, right? This quantity right here, the proportion of the state's population to the total population times the number of seats, that would be the standard quota. So the state's quota minus the standard quota in absolute value. Hamilton will minimize that, and it will minimize those other things. We'll show all that. So same thing here. These are mostly relatively speaking, and we'll get into globally in a bit. That's the minimizations here. The paper, I'll have a link here so you can get to the paper. It's from, I think, 1920 or so, written by Huntington. I think Hill may have first proposed it, but he didn't quite have the math to show the optimization that Huntington did. So if you click on this link, we'll get to apportionment. So this was done, in 1920. And the method started to be used, I believe, in 1940. But basically, so equal proportions is what he called it, and he looked at relative. So you can look at absolute difference or relative difference. So for example, 15 being 5 more than 10 is relatively more important than 250,005 being 5 more than 250,000. So the arguments for relative difference here, and it shows what each state optimizes. So what does Huntington Hill optimize? A little more clearly, well, you can look at it in different ways. We'll look at it through the people per seat of each state. So we have that here, people per seat. And if you compute that, let's look at where they're different. So Huntington Hill, it was different. I'll start with from Dean's method, or rounding by the harmonic mean, than Idaho and Minnesota. So those were the only two states that were different. So if I look at what I've got here, with Huntington Hill, Minnesota gets 8 seats, Idaho 2. Here's the population of each state. You can find the people per seat just by dividing. And I get these quantities here. If I take the absolute difference of the people per seat by subtracting these numbers, taking the absolute value, Huntington Hill, and compare it to the harmonic mean or Dean's method way of doing it, then Dean is guaranteed to minimize that. So that's the absolute difference. So Dean will minimize that. But if you want the relative difference, what we have to do is take that difference and divide by the smaller amount, smaller people per seat, which in this case is from Minnesota. So if you take that absolute difference, divide by the people per seat of Minnesota, then we get this decimal right there. So that's the relative difference between the states. Using Dean's method, if you take the absolute difference, which is smaller, but then divide by the smaller people per seat, we get this decimal right there, and that's a bigger value. So the relative difference goes up. So we can only compare one state to another, not to the whole at large. So the people per seat for each state gets relatively bigger if you switch away from Huntington Hill. So it went from that, at least for these two states, and then everywhere else it matched, so there's no point in comparing. But it went from that to here. I did the average as well, so if you were to do the total, that'd have to be a double sum. So I didn't do that on Excel, but if I do the absolute difference divided by the biggest people per seat number, then I get this value for Huntington Hill, and then if I take that absolute difference divided by the bigger people per seat, then I get this number. And so if I average these two, I'd be involved in the double sum. Again, Huntington Hill, I have a smaller average, right? Because comparatively, this number is smaller than that number. This number is smaller than that number. This one's the actual relative difference. You divide by the smaller number. So these two are the relative differences, but I did the other division as well. And again, this average, so Huntington Hill is guaranteed to minimize that. Or if I compare Huntington Hill with, say, Webster, now there's a few choices that could be made. So Montana is different New York's different, Ohio's different, and Rhode Island's different. So lots of ways we could kind of change things. If we look at, to go from Huntington Hill to Webster, you'd probably take a seat from Montana and give it to either New York or Ohio, or take a seat from Rhode Island and give it to New York or Ohio. So, but any of those changes, let's see, that would be, here's all 4 of them. So the Huntington Hill apportionment, the population to get the people per seat is right here. And then the relative difference would be this number right here, where you have to divide by the smaller one, so it's actually this one. But the relative difference with Webster, so if I made this switch, taking a seat from Montana, giving it to New York, the relative difference is going to go up, and then if you do the other division, it goes up as well. So Huntington Hill's guaranteed to have a smaller average, because always comparatively each number is smaller. So if instead we take a seat from Rhode Island, give it to Ohio, to go from Huntington Hill to Webster, people per seat, relative difference, you take the absolute difference, divide by the smaller number, so it'd be this value. And if I do that with Webster, the people per seat with this apportionment divided by the smaller number would be this number, so this number is bigger. So Huntington Hill is a smaller relative difference, and if instead I did that absolute difference divided by the bigger number, this is smaller anyway, so then the average of these two is definitely smaller. One thing that may not be as well known though is you can still do a relative difference, but you take the relative difference of each state and compare it to the ideal, the people per seat, which is the standard divisor for the whole country. That's the 761,000 value. So take this relative difference, subtract it from the ideal, divide by the 777,000. So that's the people per seat. So if you compute this relative difference for Huntington Hill, and I'll do it for each of the 2 states. That is, I'll take the state's people per seat, subtract it from the country's people per seat, divide by the state's people per seat. So that's the relative difference to the ideal. And I'll get these 2 numbers. So here you might want to do it for each state. And if I do it for the 2 states with Webster's method, these are actually smaller, and the average will be smaller. I usually compute the average. You're guaranteed the average will be smaller. It is possible sometimes one's bigger and one's smaller, but then the net sum or net average will be smaller for Webster. So let me repeat that. So if I look at Ohio and Rhode Island again, people per seat is right here. So this is with Huntington Hill. Subtract that from the ideal or the standard divisor, people per seat for the country, divide by the state's people per seat. So that's the relative difference to the ideal for that state. It's this number. And then for this state, Rhode Island, it's people per seat subtracted from the country divided by the state's people per seat gives me this number. So that's this state's relative difference to the ideal. But if I look at the Webster's apportionment and I take the people per seat, subtract it from the ideal, and divide by the state's people per seat, this is the relative difference for that state to the ideal. And for Rhode Island, here's its people per seat, subtract from the ideal, divide by the state's people per seat, here's this number. Again, comparatively, each number is smaller, so of course the average is smaller. And we can show that Webster is guaranteed to minimize this relative difference here. The people per seat for each state from the country's people per seat, relatively speaking, so divided by the state's people per seat. So on the left, that's what we're looking at. So Webster is going to minimize this sum. So that's the relative difference of the people per seat from the country's average, from the ideal, relatively speaking. So Dean minimizes the numerator, the sum of that, but relatively speaking, Webster will minimize that. But Hamilton jumps in anyway. If you multiply this quantity by the number of seats each state gets, all of a sudden Hamilton will minimize that. Now in this case, Hamilton and Webster are actually the same apportionment. So if we look at some other apportionments where they're different, so here in 2010, Hamilton is the same as Huntington Hill, but different than Webster. If we look at the Huntington Hill versus Webster, so they only differed from North Carolina and Rhode Island. If we look at to each other, the relative difference, here's Huntington Hill apportionment with the population, so the people per seat for those two states, relatively speaking, take the absolute difference, divide by the smaller number, we get that value. If I do it with the Webster, I get this value to people per seat. If I do the other one anyway, again, Huntington Hill will have a smaller value. So the average, of course, will be smaller with Huntington Hill. But if we compare, relatively speaking, to the ideal, the people per seat for the country in 2010 would have been 711,000-ish. Here's the people per seat. Subtract it from the country's average, divide by the state's people per seat. We get this relative difference for Huntington Hill. But with Webster, with North Carolina, well, we get a bigger number here. But if you look at Rhode Island, we'll get a smaller number in such a way that the sum or average is smaller with Webster. So these two numbers are closer than these two numbers, and this one's smaller. Anyway, so the net average is smaller with Webster. And so if you compute the total relative difference each state's people per seat is to the ideal, Webster will minimize that. It's smaller than Dean, it's smaller than Huntington Hill, it's smaller than Hamilton. There's the values. If I look at the one with Gauss in between Huntington Hill, so I can compare Huntington Hill to the Webster, to the Gauss, arithmetic geometric mean. Again, so relative to each other, so one state to another divided by the smaller people per seat. Huntington Hill will be smaller, and even with the other one, it'll be smaller. So the total average, if I were to do a double sum, Huntington Hill is smaller than that arithmetic geometric mean. So that's what Huntington Hill minimizes. It's kind of complicated. You can only pairwise compare. So pairwise, relative to each other, Huntington Hill minimizes. But to the ideal, it's still relatively speaking, Webster is better. So again, if we compare to the people per seat for the country, this is a hypothetical here, but it's still the math shows what's going on. Webster will have a smaller average. In this case, Webster was smaller comparatively as well. And same with over here. So Webster beat out the arithmetic geometric mean. And if I compare the relative difference for every state to the ideal, so population of each state divided by the seats for each state minus for the country divided by the state. Webster will minimize that. Again, Dean minimizes the numerator. And Huntington Hill minimizes relatively speaking. That's right here. There's the Gauss. That was close, but a little bit off. And one last one. For 1990, again, Hamilton will be different than Huntington Hill and Webster. There's the relative. I didn't do pairwise comparison here, but just Webster is the minimum there, which is different than Hamilton and Huntington Hill. So close, but Webster is the smallest. Look at the numbers long enough. But if we multiply each state by how many seats there are, now Hamilton will actually minimize that. So it's kind of a relative difference. But how many times did it happen, right? So maybe you want to count California 52 times if it gets 52 seats. So Hamilton will minimize that. Here we go. So lastly, I'll show those things that I claimed about the minimum. So taking from these properties here, no time to look at them, but we get this. So this is a summary of what we had. So Adams minimizes this quantity, which I looked at these bottom ones. So the maximum of people per seat and the sum of how much you're over the country's average. Dean minimizes pairwise people per seat, just absolute value, so over or under. But that will also minimize the people per seat minus the country's people per seat. And this, which I don't know if I'll show that, but I'll show this one. So Huntington Hill minimizes a few things. This is one of them. This is the one we looked at. So relatively speaking, pairwise, people per seat. So if you make a switch, you'll increase this sum if you sum over all the states. Webster minimizes seats per person, ideally, or in absolute value, I should say, which also minimizes the seats per person for each state minus the ideal or the country's average. And so it'll also minimize this, the people per seat, not seats per people, but the people per seat, relatively speaking, from the ideal. So your difference from the country's average, relatively speaking. And Jefferson, you saw that as well. And then here's the quota. So this is really just the standard quota. SK is the quota you're given. The state's population divided by the total population, that fraction times the number of seats, that would be your standard quota. So how far away you are from that. So Hamilton will minimize that if you just let Q equal 1. I also showed it minimize these two things. So again, Dean minimizes this, but then if you multiply by how many seats there are in each state, Hamilton will minimize that. Webster minimizes this, but then if you multiply by how many people in each state, Hamilton will minimize that. And just, so here comes the proofs. So first for Dean, it minimizes this. So this is pairwise comparison, but it'll minimize to the country's average as well. And this is done by the Dean's method, as I said. The proof, you want to use the triangle inequality. You can't necessarily use it unless you know that the only switching you'll do is from one state which is under the average to another state that's over. And so it's not a hard proof, but as long as no state is having a quota violation, so no state's getting above its upper quota or below its lower quota, then it's easy to see that Dean will minimize this sum, because if two states, let's see, well, wait, scroll up. If both states are above, then they must have their lower quota, right? Because if you divide exactly by the standard quota, this is where you would be. So to be above it, you're dividing by a number smaller than the standard quota. So you must be dividing by the lower quota. So, but if both states are above, they're both at their lower quota. And so you would not take a state from one of those seats with its lower quota and give it to another state, because then that state will be below its lower quota. And similarly, if both are below, then they must have been given their upper quota. You had to divide by a number bigger than the standard quota. So as long as we know switches will only be made by states which are on opposite sides, then we can basically use the triangle inequality. And so that's the idea of the proof. So if you minimize pairwise, you'll also minimize globally to the average, based on at least if there's no quota violations guaranteed. There's the standard, the seats per person, same thing, same idea, which I didn't show. But now let's look at this relative difference to the ideal of people per seat. Well, just some simple math. We'll take this denominator, divide it into the numerator, put it into the absolute value. Well, we'll get a 1 here. This divided by itself is 1. Then minus, then P over S divided by PK over SK. Flip. And then kind of, you can flip sort of again. So this is the same thing, SK over PK over S over P. If you simplify this, you'll get the same thing. So these are equal. If you get a common denominator, you have that, and then you can factor this out. This is a constant for any fixed country once you fix the number of seats in the population. So that's a fixed number, you can factor it out. And so minimizing this is equivalent to minimizing this, and that's done by Webster's method. So that shows that. Hamilton minimizes the quota minus the standard quota. And again, if you factor out some things, so if I factor out, say, S over P, well, then I have to put a P over S here. And then factor out SK. Then I've got this sum. This is a constant out front, so that's fixed for the country. And so minimizing this minimizes this. So that's the state's seats times the people per seat minus the state's people per seat. And so that's done by Hamilton's method, because we know this is done by Hamilton's method. And similarly, if instead of factoring out S over P and then SK, if I just factor out PK, then right away we get the S over SK over PK minus S over P for the country. So again, that part Webster minimizes, but if you multiply by each state's population, Hamilton will minimize that. So it's a long-winded video, hopefully visible. You can read everything. Just close. I mean, it's kind of subjective, I should say. What's the best choice of apportionment? A lot of people think Webster is actually better. I think I like Webster more. Hamilton, even that, I think has a case. Some of the things Hamilton minimizes, you might argue, are more important than what Webster minimizes. But I mean, the only thing Huntington Hill minimized was a relative pairwise, but Webster minimized that same thing relatively, but to the ideal. So if we look at the 2020 apportionments, in this case, Hamilton and Webster agreed, and which apportionment we should choose, it's kind of a subjective choice. You know, what do you want to optimize? Do you want to optimize that relative difference each state pairwise to another? Or what about relative difference each state to the country's average? Or what if you multiply by the number of seats or people in each state? So you can make a case for Hamilton or Webster. In this case, they're equal, the same. And some do that. So if I were in New York or Ohio, I would relook at what criteria do we really think so important, and is it really fair? Because it's kind of known that Huntington Hill kind of favors the small states, as you can kind of see here, where these small states with 1.44 and 1.43 for their standard quota, they got rounded up to 2. California, I mean, if this were, again, a liquid 435 gallons, you'd give New York 26.56 gallons. Well, 27 is definitely closer. So anyway, that's what they optimize. So hope you enjoyed. Have a nice day.